In today's video at Medical Sciences, we want to discuss with you determination of glucose in urine, what we call glycosuria, or you can call it glucosuria. So we want to see what are the causes, because we know glucose is very essential in the body. It is not supposed to be excreted in the urine. So we want to see what causes glucose to appear in urine. After looking at the causes, we're going to discuss different methods whereby we can determine glucose in urine. So we are going to see that glucosuria, or what we can call glycosuria, is presence of glucose in urine. That is what we can call glycosuria, presence of glucose in urine. And this presence of glucose in urine, it is presence of glucose in urine greater than the normal, whereby in urine, glucose should not be greater than 15 milligrams per deciliter or milligrams per cent. So if you find the urine is having glucose, we are saying that glucose should be less than 15. So between 0 and 15, it cannot be even detected by any means in urine. But if it goes greater than 15 milligrams per deciliter, this is what we are calling glycosuria or glucosuria. Glucose beyond the normal levels in urine. So much as we say it is not supposed to be there, but it leaks in little amounts, but beyond it is detected, and we call it glucosuria or glycosuria. So this is what we can define glycosuria. And the causes, we have different causes of glycosuria, whereby glucose goes beyond this limit is what we are going to see. And before we look at the causes, we are going to tell you that the renal threshold of urine is between 160 to 180 milligrams per deciliter, or you can call it 9 to 10 millimoles per liter. What is the renal threshold? Substances which are absorbed in the renal tubule, they have what we call renal threshold, which is the value. This is the value beyond which these substances appear in urine in greater amounts. So that is what we call renal thresholds. So if you are a person and you have your glucose level beyond 180 or beyond 10 millimoles, it can appear in urine. That is what we call the renal threshold. And the causes, which causes your glucose level to go beyond 180 milligrams per deciliter or beyond 10 millimoles per liter, one of the causes is lack of insulin or insulin resistance. So lack of insulin or insulin resistance, this is seen in diabetes, chronic diabetes mellitus. It can either, this one, lack of insulin, that is type 1, diabetes type 1, and insulin resistance is diabetes type 2. So all these can lead to glucose appearing in urine. But the most common cause is type 1, but also type 2 can cause glucosuria. Another cause is increased glycogenolysis. Whereby there is increased breakdown of the glycogen. We know glucose is stored in the form of glycogen in the liver and skeletal muscles. So if there are trigger factors, maybe stress, conditions like stress, when you're stressed, it can trigger increased glycogenolysis, whereby it is releasing glucose, and this glucose can appear in the urine. And another thing is tubular disorders, kidney tubular disorders, whereby the tubular part of the kidney is not doing the work of reabsorbing glucose by active transport. So, for example, if this transporter is affected, sodium stroke glucose symport, this is the one responsible for reabsorption of glucose in the presence of ATP. So if it is a defect, then we can see glucose appearing in urine. And another cause can be increased glomerular filtration rate. If glomerular filtration rate, which we abbreviate as GFR, is high, meaning more of the glucose is being filtered than what the kidney tubules can reabsorb. So it can lead to appearance of glucose in urine at level beyond 15 milligrams per deciliter. So these are some of the causes of increased or presence of glucose in urine to the individual. Stress is one of them, increased glomerular filtration, tubular disorders, increased glycogenolysis, and lack of insulin or insulin resistance, which we see in diabetes mellitus. So after looking at this, so as a student, you must be knowing that glucose levels is much as it is needed by the body. Some of it which goes in urine, but should not be beyond 15 milligrams per deciliter. And another thing you have to note is that the renal threshold is this. This one is commonly asked, 160 to 80 or 9 to 10 millimoles per liter. Then you have to know at least 4 causes of glucosuria. So after looking at the causes, now we are going to look at methods of determination. How can we determine glucose in urine? And one of the methods is Clinistix. Clinistix, this one you are using a heuristic. You are using a urine strip. And this is the most accurate and specific. This is sensitive and specific compared to other methods we are going to discuss. And the principle behind this Clinistix method, is that if I have glucose in urine, this glucose is going to react with oxygen to form gluconic acid, plus hydrogen peroxide. And this reaction occurs in the presence of glucose oxidase, which we normally abbreviate as GOD. So glucose oxidase catalyzes the oxidation. This reaction is oxidation because we are adding oxygen. It catalyzes the oxidation of glucose present in urine sample to gluconic acid and hydrogen peroxide. And after producing gluconic acid and hydrogen peroxide catalyzed by glucose oxidase, we are interested in the hydrogen peroxide which is formed. That the hydrogen peroxide formed, we are on the principle. This is the principle. So the hydrogen peroxide formed, we can convert it to water and nascent oxygen. This is known as nascent oxygen. And this one is catalyzed by an enzyme known as peroxidase. So peroxidase enzyme catalyzes the breakdown of the hydrogen peroxide formed here to form water and nascent oxygen. And this nascent oxygen, which is formed at this reaction, is going to react with a chromogen. So we provide the chromogen like 4-aminophenazone, 4-aminophenazone. We provide it as a chromogen. This is a chromogen. Chromogen, chrom means the color. So this 4-aminophenazone is going to produce color when it reacts with nascent oxygen, and this color is going to be green to shades of brown. So green to brown. Shades of green to deep brown color, depending on the intensity. So it can be green, brown, or deep brown, depending on the intensity of glucose in urine. So we are going to end by saying that the green, the shades of green to deep brown color is directly proportional to amount of glucose in the urine sample. So the intenser the color formed, the more the glucose in urine. So please note this principle that we have only 4 steps, whereby step number 1, we are having oxidation of glucose to gluconic acid and hydrogen peroxide by which enzyme? GOD, glucose oxidase, don't forget that. Then after forming hydrogen peroxide, in the presence of peroxidase enzyme, which we normally abbreviate as POD, is going to catalyze the breakdown of hydrogen peroxide to water and nascent oxygen. Then when we have nascent oxygen, we are going to provide the chromogen, a color, a compound that produces color. So this chromogen is going to make this chromogen to produce shades of green to deep brown color, depending on the intensity of the glucose in the urine sample. And the procedure for this method of Clinistix, you obtain a fresh urine, then you open the container of the fresh urine, then you have also the bottle, you remove one strip and you dip in the urine, and then you remove excess. Then you leave it stand for 1 minute horizontally. After 1 minute, you obtain the bottle which has a color chart, a standard color chart, and you begin comparing to read the results. And you record in the pluses. Can it be glucose near, glucose trace, glucose +1, +2, +3, or +4, depending on the intensity. So that is what we can talk about Clinistix. So the second method we can use is Benedict's reagent or Benedict's solution, whereby the solution in the Benedict is copper 2 sulfate. We are using copper 2 sulfate solution in Benedict. And this Benedict, compared to Clinistix, it is not specific. This method is not specific. Why? Because it detects reducing sugars. It is for detecting reducing sugars. So reducing sugars include glucose. It includes lactose. It includes galactose. We have maltose. So all this can be detected by Benedict's solution. That's why we say it is not specific. So Clinistix remains the best method compared to Benedict's method. And the principle behind this, the principle of Benedict's, we are using copper 2 sulfate, and this copper 2 sulfate contains copper 2 ions. So the copper 2 ions in the copper sulfate is going to react with reducing sugars in the urine, such as glucose, and after reacting with reducing sugars in the urine, it's going to reduce this copper 2 to copper 1. This one you can call it cupric ion to Cu plus ion. So that is what happens with. So the copper 2 sulfate in the copper 2 ions and the copper 2 sulfate reacts with reducing sugars. Reducing sugars like glucose have ability to reduce copper 2 sulfate to copper 1. And this one occurs in the presence of heat. Heat is the requirement. In the presence of heat and alkaline media. And the alkaline media is provided by sodium hydroxide. So if I boil urine containing glucose in alkaline media and copper 2 sulfate, the copper 2 ions, which we call the cupric ions, are reduced by the glucose in the urine to form copper 1 ion, and this copper 1 ion formed is, it forms the shades of green, or we can say shades of green. Starts from blue, forms different colors, shades of because this copper 2 or cupric ions is blue in color, and this blue in color is changed to yellow, brown, orange, red. So it forms shades of yellow to red, and even brick red, or what you can call deep red. So we are seeing copper 2 sulfate, which is blue, is going to be reduced to yellow to red color complex, depending on the intensity. These colors depend on so the intensity is directly proportional to the amount of reducing sugars in the sample, like glucose. So don't forget this, that occurs in the presence of heat and alkaline media provided by sodium hydroxide, that when urine contains glucose, it is going to reduce copper 2 ions in the copper 2 sulfate to copper 1 ions, which is yellow to red colored complex, depending on the intensity of the glucose in the sample, or reducing sugars. So we have seen copper 2 ions, you can call them cupric ions. Then copper 1 ions, you can call them Cu plus. And cupric acids are blue in color. Cu plus is between yellow to red, depending on the intensity or the presence of glucose in the urine. So this is the principle behind the Benedict's. And whenever you are performing this test for reducing sugars, you have to ensure the procedure is that you have to assemble requirements. You assemble the requirements like Benedict's solution. Then among the requirements, you need Benedict's. You need the urine, fresh urine sample. You need the positive and negative control. Then you need also source of heat. So what you do, you're going to obtain your 3 tubes. Tube for the test, for the positive control, and for the negative control. After obtaining them, you're going to come and add 5 mils of Benedict's in each. So you come and put 5 mils of Benedict's reagent. So this is 5 mils of Benedict's reagent. You put it in each tube. After putting in each tube, you're going to come and add 0.5 mils, 0.5 mils of urine. Here I have 0.5 mils of the positive control, and here 0.5 of the negative control. This one is the one known to have urine, glucose in urine, and this is what is known to have no glucose in urine. And this is the test which you don't know. So after adding, you mix. Then after mixing, you boil. And as you start boiling in the water bath, you keep mixing, checking for the change of the color. The color is going to change from, as you're boiling, you observe the color change from blue to green to yellow to brown, from yellow to orange, then brown, then red. So these are the different color changes which occur depending on the intensity. So if it is trace, it will be green. That is trace. If it is +1, it will be yellow, +2 orange, +3 brown, and +4 red. So it depends. So you record reducing sugars +1, trace +1, +2, +3, or +4, depending on the intensity. So remember, you put 5 mils of Benedict's reagent, you put 0.5 of the test positive and the negative control, you mix, then you boil in a water bath, and you keep looking for the presence or the color change as you're boiling. It must be in alkaline media, and heat should be provided. So this is the procedure for Benedict's to determine presence of reducing sugars like glucose in urine. Then lastly, the methods we're going to look at, they are not most commonly used, but we need to know about them for also. But these ones are not looking for glucose in urine, but these ones can look for. So another thing we can see is also determination of reducing sugars, other reducing sugars, so that we can finish this together. So the methods we have used are for determining only glucose, but also we can determine other substances. We can determine other substances in urine. For example, we can determine fructose. Fructose in urine. And fructose, presence of fructose in urine is called fructosuria. Fructosuria, and this is detected in urine by the method known as Seliwanoff's test. And this Seliwanoff's test, it uses a reagent. The reagent which is used if we have urine which contains the fructose, it reacts with the resorcinol. In the present, it reacts with, actually we first react it with hydrochloric acid. That fructose in the presence of hydrochloric acid, this hydrochloric acid should be concentrated, and we heat, we form a furfuroaldehyde. And this furfuroaldehyde formed reacts with resorcinol. It is a reagent to form a red colored complex. And this red colored complex, its intensity is directly proportional to the amount of fructose in urine. So this is the principle for Seliwanoff's test for determining fructose in urine. That if there is a fructose in urine, when you boil it or heat it with concentrated hydrochloric acid, we form a aldehyde which reacts with the resorcinol reagent to form a red colored complex, which is intensity is directly proportional to the amount of fructose in the urine sample. So this is the method we use for determining fructose. Then lastly, another monosaccharide we can determine is pentose in urine, determination of pentose in urine. And the presence of pentose in urine is known as pentosuria, and we can also determine it in urine by the method we use is we use Bial's method, whereby this Bial's method, that if there is pentose we are suspecting in urine, it reacts with the conc hydrochloric acid to form a aldehyde. This one is in the presence of heat. And this aldehyde formed reacts with oxino. When we react it with oxino, we form a green colored complex. And this green colored complex formed depends on the intensity. The more the pentose in urine, the more the green color is formed. So the intensity of the green color formed is directly proportional to the amount of pentose in urine. So remember, here we are using oxino, then in Seliwanoff's we use resorcinol. So that is the difference. Then another difference, here we form a red colored complex, here we form green colored complex. So don't forget that. This is for Seliwanoff's, this is for Bial's method for determination of pentose, Seliwanoff's for determination of fructose in urine. So this is what we can discuss in this method, where in this session where we have looked at different causes of fructose, different causes of glucose in urine. We have seen different methods like Clinistix Benedict's reagent, and we have gone to look also at determination of fructose and pentose in urine. Fructose using Seliwanoff's and pentose used for Bial's, whereby Bial's method looks for pentose. So thank you for learning with us from the beginning until the end. We are always privileged to serve you in this field of academia. Thank you so much.